In this video, we talk about inference on paired data. This is our overview slide, which we'll spend 5 minutes or less over before we go over each topic in more detail and with examples. So first we look at paired data. That's two sets of observations are paired if each observation in one set has a special correspondence or connection with exactly one observation in the other data set. So an example is Amazon prices, comparing Amazon prices to prices in a college bookstore. We will then talk about inference for paired data. We'll analyze a paired data set. We will simply analyze the difference. Is there a difference between these Amazon book prices versus the prices at the bookstore? We can use the same distribution techniques from our previous video for the t distribution. We have our standard error, which is the x of the difference between, that's the mean x, the difference of the two prices is equal to the standard deviation of the difference divided by the square root of n, the sample size. So this is going to be the example we will look at in our video to illustrate this technique. So that concludes our overview, so we'll start taking a closer look at paired data. So paired data is two sets of observations are paired if each observation in one set has a special correspondence or connection with exactly one observation in the other data set. The example we will use is an earlier edition of the OpenIntro Statistics textbook was found on Amazon, where prices were on average lower than those of the college bookstore in 2010. So we took 210 class textbooks as a sample, and we did this using a simple random sample, and of those 68 were found on Amazon, and a portion of that data set is shown below. So we have 68 books, and we didn't list all 68 books. We can see at the campus bookstore this textbook for American Indian Studies was $47.97. On Amazon, it looks like it's a little bit cheaper. It's 52 cents cheaper. And then you can see the rest for the other books here listed. So each textbook then has two corresponding prices in the data set, one for the bookstore and one for Amazon. These sets of observations are said to be paired. When calculating the price difference here, we always subtract using a consistent order. So these all happen to be positive, and that's because we always, in this case, for these cases, the bookstore prices was always more expensive than Amazon. So we always subtract Amazon from bookstore. So bookstore minus Amazon to get the positive difference. If it happens that the bookstore is cheaper, we will get a negative price difference. And it's important to keep the negative if the bookstore is cheaper, because that will signify it's the bookstore that's cheaper. So Amazon prices are always subtracted from, in this case, the bookstore was the UCLA college bookstore. While we did not list all 68 textbooks, we do have a histogram here. You see there are a few books with the negative between -20 and 0, and that indicates where the bookstore was cheaper because it's bookstore minus, where bookstore was cheaper because it's bookstore minus Amazon. Since Amazon was greater, there was a negative number. But you can see for the most part, Amazon is cheaper, but not by a lot, but by a little bit. Like here, you can see the price difference generally is less than $1. Every now and then you'll get something that's $3, but you can see there's a very few books out here where it's actually significantly cheaper on Amazon. I got rid of that table and the histogram to give us more space, but I do have summary statistics for the 68 sample price differences. There were n is equal to 60. The price difference is 3.58, so on average, you can save $3.58 by shopping on Amazon. And the standard deviation was 13.42. And the first thing is to check conditions for whether we can move forward with the test using the t distribution. Remember, for the t distribution, we want to have independent samples or observations. But here we were told this was a simple random sample. And then second, we also want to see that the data set size, if it's n less than 30, we have to check that there's no real extreme outcomes. Here, our sample size is 68, so that looks pretty good. But let's just take another look at that histogram. It's also worth noting there are no extreme outliers. There are these two things here that, there are gaps. So there is like this jump over here, but this isn't one single book. It's like a little clustering. And here's another little cluster. So in that way, even though the data is spread out with gaps, these here, you can see that the measurements are very similar to these measurements here. They're not considered one or two unusually large measurements. By the time you have a little cluster of measurements, it's not so much an outlier, especially when n is equal to 68. So, 3 measurements, it's 5% of your data. So the point is that, one, we have a large sample size, and there are no extreme outliers. Now that we've checked conditions for whether we can move forward, and we did satisfy the central limit theorem, we can perform the hypothesis test. So our hypothesis is then that there's no price difference. On average, our the average price difference is going to be 0, which means our alternate is that the price difference is not equal to 0. The next thing I'm going to do, because it's easy to do, I'm going to calculate my standard error. So that's S of our difference divided by our square root of n. So our standard deviation is equal to $13.42 divided by square root of 68. So that gives us 1.63. The next thing I'm going to calculate is our test statistics. That is our t-score, what I'm going to call our t-score. So that's going to be our actual difference that we found in our sample, which is 3.85. This is not a 13, that's a parentheses. So our sample is 3.58, and the difference between 3.58 and our hypothesis is equal to 3.58 minus 0 divided by my standard error. That's 2.20 standard errors higher than what our hypothesis would predict. Again, our sample shows us a mean that's 2.20 standard errors higher than the hypothesis has for our mean. I should also show calculation for degrees of freedom because it's easy. It's n minus 1, so degrees of freedom is 67. So my table does not go to degrees of freedom equals 67, so I just use statistical software, and the one-tail area for degrees of freedom is 0.0156. So this is my picture. At the upper tail, I have 0.0156. But look at our hypothesis. It's not just about being greater than this t-score. It's not equal to, right? Which means we also need to take the second tail. So we need to calculate that x is either greater than 0, which is this tail, or less than 0, which is this other tail, the lower tail. So we need to double our 0.0156 area. So we're going to get a p-value of 2 times 0.156. So we get 0.0312. So now our p-value is 0.0312, which is less than our required 0.05. So if H0 is true, there's only a 3% chance of producing a sample with a mean of 3.58. And 3%, we generally want something like 5%. So we're going to reject H0 and say there's probably a real difference in price. So I cleared out this data, but I did keep some of my calculations here so we can create a 95% confidence interval for the average price difference. So if we want 95% of our data in the middle, that means we have 5% left between the upper and lower tail, meaning each tail is 2.5%. For 67 degrees of freedom associated with a 95% confidence interval is going to be 2, so our t-score is 2, which will then give us our confidence interval is going to be our mean, 3.58, plus or minus 2 times our standard error, 1.63. So we have our interval is 0.32 to 6.84. So we're 95% confident that the mean is between 0.32 and 6.84. To review what we covered in this video, we looked at paired data, and paired data is when we have two sets of observations are paired. If each observation in one set has a special correspondence or connection with exactly one observation in the other data set. So when we analyze paired data, we're going to analyze the difference. In other words, subtract one observation from the other. We can use the same t-distribution techniques from our previous video, and we're going to use that same standard error. The standard error now on the mean difference is equal to the standard deviation for the difference divided by square root of n, where n is the sample size. And we completed this hypothesis testing example as well as a confidence interval. So that's it for this video. Thank you for watching.